Hi, we will continue our discussion on using cost function curve to find the parameters of linear regression model. Now by the end of this video, you will be able to explain how cost or loss function curve can be used to find the parameters of the linear regression model and explain the need for gradient descent algorithm. Using our cost function curve, we can now easily find the optimum value of slope m, 234 in this case, for which the cost would be minimum as shown on the plot. This value was calculated from the cost table using the minimum function. Now that we have the optimum value of m, does that mean we have our best fit line or the best fit linear regression model for this problem now? We are missing something. Can you guess what it is? Yes, intercept c. We have been calculating the cost with respect to only the slope m of the line and not the intercept c. Can you imagine what the cost function curve would look like if we consider both slope m and the intercept c? We would get a three-dimensional curve as shown below, minimum value of which will depend on both the slope m and the intercept c. Now, you can clearly see that even when the cost function is three-dimensional, with respect to the intercept c and the slope m, it still has the bowl-shaped curve and has the global minima represented by the blue color. We define a function intercept error, which is very similar to the slope error that we had defined before. You might have already guessed that this function is for finding the right value of the intercept, just like what we did for slope. Now, let's try to find the optimum value of c manually. For this, we will keep the value of m as constant 234 and now we'll change the value of intercept c using the same method we followed for finding optimum slope. We have named this function intercept underscore error. Next, we define the range of values for the intercept, that is, different values of intercept for which we would want to compute MSE. We name this list as intercept. Now as you can see, this list contains values between 5000 and 50,000 in steps 1. Like we did previously, we follow the same procedure as making a cost table for the intercept errors and visualizing it. Looking at this cost function curve for intercept c, we can now find the optimum value of c for which the cost would be minimum, and as per this plot, the optimum intercept value is 10834. So now we have the optimum value of m and optimum value of c. Does that mean that we now have the ideal pair of m and c which represents the best fit line? You may be tempted to think that we do, but let's find out. Now let's repeat the process of finding optimum value of m, but this time we would keep intercept c as 10834. We get a new cost function curve when c is 10834 as shown below. Now as you can see, we get the new optimum value of slope as approximately 229, which is different than what we got earlier. This means that the optimum value of slope would depend on the value of intercept and vice versa. If we were now to again find out the new optimum value of intercept C using the new optimum slope as 229 using the same procedure as before, we will get the updated intercept value as 19199, which is quite different than the value of intercept that we got earlier. Now we have to repeat the cycle a few times before the values of M and C converge to their respective optimum values. That is, any further repetition of the above cycle does not result in any significant changes in optimum value of M or C. In our case, we find those values to be 219 for M and 39428 for C. Hence, we can say that the equation of our best fit line or the best linear regression model is y equal to 219x plus 39428. So we have now learned how we can find the ideal slope and intercept of a line manually by identifying the optimum value of the slope, M, and the intercept. But we could do this because our data had only one input variable. But what if our data has several input variables, that is x1, x2, xn, which means the equation of the resultant linear regression model would be that of a line in n-dimensional space like shown here. Y is equal to c plus m1x1 plus m2x2 plus m3x3 and so on till mnxn, where x represents the ith independent variable and m represents the slope corresponding to that independent variable. It is not possible, or rather would be very tedious, to calculate the ideal values of m1 to mn and intercept c manually as we did before. To counter this problem, we will learn about the concept of gradient descent algorithm, which helps us to find the ideal value of m corresponding to each and every independent variable automatically. And we will learn about it in the next topic.